Greetings, this is Rob, Chief Flight Instructor for VATSTAR.com, and in this lesson we'll answer the age-old question, what makes an airplane fly? Now to keep the video at a reasonable length, I'm going to go through it kind of quickly, so pause and rewind as you need to, and if you still have questions, my contact information will appear at the very end. Let's start with a few vocabulary words. Airspeed. Well, that's the speed at which the airplane travels through the air. Duh, that might sound obvious, but it's not the same as the speed as traveling over the ground, and we'll get into the difference in a later lesson. Lift. That's the upward force that a wing generates as it moves forward through a stream of air. When we talk about a wing, sometimes we talk about its leading and trailing edges. So here's our little Cessna Skyhawk, and this is the leading edge of the wing. Okay, likewise, the trailing edge is back here, closest to the tail. And the very front of the airplane is referred to as its nose. Very nice. Finally, thrust refers to how much pushing power the engine is generating. Now, lift. Like we said, that's generated when the wing slices through a stream of air. Now, if you're not curious how that happens, you can zone out for a few seconds, but bring it back in about 2 minutes and 25 seconds into the video, okay? So, how does the wing generate lift? Well, there are two forces at work here, the Bernoulli principle and Newton's third law of motion. Alright, now here's our wing, and it's traveling forward toward the left of the screen. That means the stream of air is passing it over it left to right. Notice how the wing is more curved on the top surface than on the bottom? The air flowing over it has to take a longer path, so it speeds up. That makes it exert less pressure against the top of the wing than the air on the bottom of the wing is exerting, which creates a partial vacuum that the wing then rises to fill. And there you have it, the Bernoulli principle. Now, at the same time, that same wing traveling in that same direction also has a slight uptilt to it. The air hitting the bottom is therefore deflected downward slightly. Now, you remember Newton's laws from physics class, right? The whole equal and opposite reaction stuff? Okay, so air goes down, wing goes up. Voila, Newton's third law of motion. How much of your plane is being held up by Bernoulli and how much by Newton? Well, that depends on the particular aircraft and the exact shape of the wing, and sometimes it changes depending on the situation. So, the good news is, unless you're designing the things, from a pilot standpoint, it really doesn't matter. You don't really need to know how lift is generated, just that it is. So, if you were with me up until this point, you're good. Okay, everybody back with me? Great, moving on. Angle of attack refers to how tilted the wing is in relation to the airstream it's moving through. Now, be careful, that doesn't mean its angle relative to the Earth. What I mean by that is, take these two wings and tell me which one has the higher angle of attack. Well, you might say the second one on the right because it's tilted up higher. But the answer is, you don't have enough information. It depends on the angle of climb or descent. If the one on the left is descending, that's a very high angle of attack, and if the one on the right is climbing, that's a relatively small angle of attack. Now, in rare occasions, angle of attack can be negative. That's when the leading edge of the wing is pointed below the direction of the aircraft. That's usually a very, very temporary and fleeting situation that happens when you pitch the nose of the plane down suddenly. You usually only encounter that in aerobatic or air combat maneuvers, and only in recreational or commercial flying if something is going horribly wrong. Anyway, where was I? Oh yeah. Stalls. A stall is what happens when the angle of attack gets too steep. The wing stops slicing efficiently through the airstream and is now just mashing through it. And when that smooth airflow goes away, so does pretty much all of your lift, and you're going to start dropping out of the sky, because now you're not an airplane, you're a piano or an anvil. Now, a stall in aviation terms refers to the stalled airflow of the wings. It has nothing to do with the engine stopping. When a car stalls, you're talking about the engine not having enough RPMs to continue running. When a wing stalls, the plane's engine might be functioning completely normally. In fact, lots of crashes have occurred due to stalls where the plane's engine was operating perfectly right up until impact. A lot of news reporters don't understand the term, so you'll hear maybe the investigating authority will say something about a stall and the reporter will make some sort of mention about the engines not running, and only us pilots that are watching, and pilot wannabes, I guess, will know the reporter doesn't know what he or she is talking about. So listen out for that next time. It'll drive you nuts from here on out, I promise. So, regulating lift is done in one of two ways. Starting in straight and level flight, meaning you're at a constant altitude, you're neither climbing nor descending. That means the amount of lift your wings are generating is perfectly matched to the airplane's weight. To increase the lift, you have two choices. You tilt the wings further up or increase the airspeed. So here I am in my Cessna Skyhawk, level 1,500 feet. Notice how nose up I have to be at this speed to maintain altitude. I'm just over 50 knots, which is slightly above the stall speed of the aircraft in this configuration. So now I'm increasing the throttle to show how you can trade off airspeed for angle of attack. As my airspeed increases, I need much less of an upward tilt to maintain the same altitude. The faster I go, the more nose down I can fly and still maintain 1,500 feet. Here's a nice split screen view so you can see how much more nose up I was at the beginning. Remember, I wasn't climbing. I was level at 1,500 feet in both instances. This is all about the difference in angle of attack. So knowing what we know, how do we regulate lift and avoid stalls? If a stall's impending, your aircraft will have a warning of some sort. It might be a horn or a buzzer, or in some fancy planes a voice that says, "Stall, warning." Lots of times there's a mechanism that causes the control stick to shake, although if you're flying with a $20 joystick like I am, I'm guessing that's not going to have that feature. But when you're trying to climb and you're starting to fall, your instinctive reaction is going to be to pull the nose higher. Since most stall situations are created by low airspeed, the thing to do is to lower the nose and increase the thrust. Getting the nose lower does two important things. It reduces the angle of attack, and it gets your plane pointed in the direction it wants to fall anyway. That, plus the increase in thrust, will get the smooth airflow going over the wings again, and then you can pitch back up and recover the lost altitude. Now, like we said before, stalls aren't always due to low airspeed. High-speed stalls happen when you pitch the plane up suddenly, and the direction it's pointed changes more quickly than the direction it's going. Its nose is higher, but its momentum is still carrying it in the original direction. It's still going to stall, but it's not going to start automatically pitching nose down, so getting it facing the way it's falling is going to be a challenge. And it's a challenge that you might not survive unless you're sitting at your computer in an office chair like I am. So avoid those high-speed stalls by being gentle with your airplane and not yanking the nose up drastically. Alright, so let's quickly summarize the key points. Wings generate lift by slicing forward through the air. Angle of attack refers to how tilted the leading edge of the wing is against the direction of the airflow, not against the horizon. You can increase lift by increasing the angle of attack to a point, or increasing the airspeed. When you get to the critical angle of attack, the wing stalls and the amount of lift created drops off suddenly and severely. Most stalls are recovered by lowering the airplane's nose and increasing thrust. Got it? Good. If you have any questions, shoot them over to me in an email to cfi@vatstar.com. We'll see you in the skies.